We learned earlier the kinematics of rotational motion. Now we are going to discuss the dynamics of rotational motion. From Newton's second law, we learned a net force causes acceleration on the body. Force can also cause rotational motion on a rigid body, rotating about an axis. This tendency of a force to cause or change the rotational motion of a body can be measured in terms of a quantity called torque, denoted by the Greek alphabet, tau. You are exerting torque every time you open the door of your refrigerator, twisting the bottle cap of your favorite mang tomas sauce, fastening a nut by means of wrench, or even when you cut your long nails. To illustrate what torque is all about, consider a door, in this figure, viewed from top, with length L. This length is the distance between the hinge and the door knob. To open a door, we usually apply a force F on the door knob, perpendicular to the length of the door. Thus, we are exerting torque on the door. Mathematically, the magnitude of torque is expressed as the product of the force F, and the perpendicular distance L, called lever arm, between the line of action of the force, and the point of rotation O, called pivot or fulcrum. The SI unit of torque is Newton meter, for as long as the unit of force is in Newton, and the lever arm is in meter. It can also be expressed in pound-inch, pound-foot, and dyne centimeter, in other systems of unit. Torque is a vector quantity. Its direction can be determined by how the body rotates. When the force tends to rotate the object counterclockwise, torque is a positive value. When the force causes the object to rotate clockwise, the torque is a negative value. Always remember the sign convention of torque. Torque varies with the lever arm L, and the relative angle of the line of action of the force F, from the lever arm. Remember, torque is at maximum value when the force F acts perpendicular with the lever arm, that is, the angle of the force F, and the lever arm L is 90 degrees. When the force F acts at an angle theta, from the lever arm, we will consider only the component, which acts perpendicular to the lever arm. In the figure, only the y component Fy acts perpendicular with the lever arm L. The x component of the force causes no torque since the line of action of this component force hits the fulcrum. In this case, torque is expressed as force F, sine of the angle theta, multiplied by the lever arm L, wherein the angle theta is the angle between the force and the lever arm, measured in degrees. Here are additional important notes to consider. When the force F acts parallel to the lever arm, or when the force acts directly on the fulcrum, torque is zero. It means that the body will not rotate, even if we Let us answer this first problem about torque. Problem number 7. In the figure below, a force of 10 newtons is applied to a wrench to tighten a nut. The length of the wrench is 0.2 meters. What is the torque exerted when the force acts, letter A, at the end, and letter B, in the middle of the wrench? Letter C, if the force is acted 30 degrees from the lever of the wrench, determine the torque. Okay, we list down the given information. The magnitude of the force is 10 newtons, and the lever arm of the wrench L is 0.2 meter. And for letter C, we have 30 degrees. What we need to look for is, letter A, the torque when the force is acting at the end of the wrench. Letter B, the torque produced when the force acts at the middle. And letter C, if the torque acts at the end 30 degrees from the wrench. Now, we are ready to solve. For letter A, so this is very easy. We apply the formula of torque, force times lever arm. But before you use this formula, make sure to check if the force F is already perpendicular with the lever arm L. So 10 newtons times 0.2 meter, the torque of the force about the center of the nut is 2 newton meter. For letter B, we use again the formula, torque equals force times the lever arm, but this time the force is acting at the middle of the wrench, so the lever arm is only 0.1 meter, then multiply it with 10 newtons, so the torque produced by this force, acting on the middle about the center of the nut is 1 Newton-meter. Lastly, for letter C, since that the force is acting 30 degrees from the lever arm, so we use the formula, F sine of the angle theta, multiplied by the lever arm. Substituting the given information, 10 newtons sine of 30 degrees, multiplied by 0.2 meter, so the torque is 1 Newton-meter. As you can see, the answer in letter B and C are the same. Can you tell why? We learned that a body can rotate, either in counterclockwise or clockwise direction, depending on the orientation of the force relative to the lever arm. But, what if there are two or more forces acting on the lever, just like as shown in the figure? In what way or direction it will rotate? Will it rotate counterclockwise or clockwise, or it does not rotate at all? These questions can be answered by computing the net torque acting on the body about the specified fulcrum. This is analogous with the superposition of forces we have discussed in Unit 1. The net torque, denoted by summation of tau, acting on a body is equal to the summation of individual torques produced by individual forces acting on a body. When the net torque is a positive value, therefore the body rotates counterclockwise. When it is negative, then it rotates clockwise. If the net torque is 0, then the body will not rotate. We will study later in more detail the situations wherein the net torque at any point in the body is 0. Okay class, let us keep up. Problem number 8. A lever of length 15 centimeters is subjected simultaneously with 4 forces as indicated in the figure below. Determine the magnitude and directions of the net torque at letter A, point A, and letter B, point B. So we list down all given information. Force F sub 1 is 10 newtons that acts 60 degrees from the lever. Force F2 is 20 newtons, which acts perpendicular with the lever. Force F3 is 20 newtons, and F4 is 10 newtons, both act perpendicular with the lever. So we are going to solve for the net torque produced by these forces, about point A and point B. For letter A, now we imagine that the fulcrum is point A, as shown. It means that we will have based the measure of the lever arm of each force at this point. The net torque about point A is equal to the summation of torque produced by each force, T1, plus T2, plus T3, and plus T4. The torque T1 is already 0, since 10 newtons is already acting at point A. It has no lever arm. The torque produced by F2 is a positive since it tends to rotate the lever counterclockwise, which is 20 newtons times its lever arm from point A, 0.05 meter. Then, the torque produced by F3 is also positive, since it tends the lever to rotate counterclockwise. So 20 newtons times 0.1 meter. Then, this is negative torque, since the force F4 tends to rotate the lever clockwise, that is negative 10 newtons times its lever arm, 0.15 meter. So pressing all of these in your calculator, the net torque about point A is 1.5 Newton-meter. Since our answer is positive, the lever will rotate counterclockwise, if the fulcrum is placed at this point. That's it. Do you have questions in mind? Do not hesitate to ask me in our Google Classroom or group chat. Let us keep up. For letter B, we place the fulcrum at point B. Again, all lever arms will be based about this point. The torque produced by F1 is negative 10 newtons sine of 60 degrees, multiplied by its lever arm from point B, 0.05 meter. This is negative, since it tends the lever to rotate clockwise. Then, the torque produced by F2 is 0 because this 20 newtons already hits the fulcrum B. Then, plus the counterclockwise torque produced by F3, positive 20 newtons times 0.05 meter. Then finally, the negative clockwise torque produced by this 10 newtons, multiplied by its lever arm from point B, 0.10 meter. So the net torque about point B is 0.15 Newton-meter. The answer is also positive, therefore the lever tends to rotate counterclockwise when the fulcrum is placed at point B. Now, let us check what have you learned. Exercise number 4, determine the net torque about point C and point D in the lever shown below. Good luck. We learned from Unit 1, that when there is no net force acting on a body, the body remains at rest when it is initially at rest, or it will remain in motion at constant velocity, when it is initially moving. Here, we will extend this idea by considering the state of rotational motion of a body. Here, we will analyze bodies in equilibrium condition. The body is in the state of equilibrium when the body satisfies the two conditions, translational equilibrium and rotational equilibrium. To explain these two conditions for equilibrium, consider a 2-meter-long uniform horizontal lever that is supported by a hinge at its center. Then we suspend 50 N of weight at each end of the lever. By simple reasoning, of course, we say that the lever is balanced, or it does not move nor rotate. Actually, this state of balance means the lever already satisfies the two conditions for equilibrium. The first condition, translational equilibrium, is actually based on Newton's first law of motion. When there is no net force acting on a body is zero, the body remain at rest. If we draw the FBD of the lever, we see that the two 50 Newton downward weights are being balanced by the upward force 100 N, exerted by the hinge. The force exerted by the hinge is termed as reaction. Without this vertical reaction, the bar will definitely accelerate downward because of the two weights acting at its ends. Now, if we consider the summation of force on vertical axis, or y-axis, the result is zero. And since there is no net force acting horizontally, or along x-axis, we may say that the lever satisfies the condition of translational equilibrium. On the other hand, rotational equilibrium is the condition in which the net torque acting about any point of rotation on the body is zero. Here, if we take the net torque about the fulcrum O, the 50 N weight on the left end produces 50 Newton-meters of torque, while the other 50 N weight produces negative 50 Newton-meters of torque. Since the reaction 100 N directly acts at point O, it does not create torque about this point. With these, the net torque is zero. Remember, to attain fully the state of equilibrium, these two conditions must be satisfied. In problem solving, the first thing you need to do is to draw the FBD of the body. Then decide which of the three equations of equilibrium is applicable. Sometimes, it is necessary to use two equations simultaneously to solve the unknown variables. Now, let us answer problem number 9. This problem deals with conditions for equilibrium. A meter stick is supported at its center. It is balanced by two weights, A and B, as shown in the figure below. Letter A, if the weights of A and B are 40 newtons and 20 newtons respectively, find the distance of weight B from the support. Letter B, what is the reaction force in the support? We established the given information. The weight of A is 40 newtons and for B, 20 newtons. What we are going to solve is, letter A, the lever arm of B from the support, to maintain equilibrium, and we label this as D. And for letter B, we are going to solve for the reaction force in the support R. Before we solve, let us draw the free body diagram of the meter stick. So this is the meter stick. We label the location of the support as point O. Then we indicate all the forces acting on the meter stick. So we have these two downward forces, 40 newtons and 20 newtons. This 40 newtons is located 20 centimeters from the support. We do not know yet the numerical distance of this 20 newtons from the support, so we just label it as D, and this is what we are going to find out in letter A. Then, the support should exert an upward force, called reaction force, in order to counterbalance these two downward forces. This reaction force keeps the translational equilibrium of the meter stick. Now, we are all set. For letter A, we use the equation for rotational equilibrium, that is, summation of torque about the support, point O is 0. Let us observe. About point O, this 40 newtons tends to rotate the counterclockwise, so its torque is a positive value. The torque produced by 60 newtons is 0, since it already hits the fulcrum, O. The torque produced by 20 newton force is a negative value, since it tends the lever to rotate clockwise. So we expand this equation as 40 newtons times its lever arm from point O, 20 centimeters, minus the torque produced by 20 newtons, times the unknown lever arm D, then we equate this to 0. Then we solve for D, with a little algebra will give 40 centimeters. So this is the distance of the 20 newton weight in order for the meter stick sustain equilibrium. For letter B, we are going to solve for reaction in the support R. We only use the translational equilibrium equation along vertical axis, that is, summation of forces along y equals 0. So we have R, minus the two downward weights 40 newtons, and 20 newtons. Be careful on signs. These are negative since these two forces are downwards. Then solving for R, it gives 60 newtons. Any questions, class? Come on, you can ask your teacher. Don't be shy. Let us consider another sample problem. Problem number 10. Kent and his mother sit on one side of a seesaw, while Charles and his father sit on the other side, as shown in the figure below. Letter A. How far from his father should Charles sit so that the seesaw is balanced? Letter B. What is the reaction in the fulcrum? Neglect the weight of the seesaw. So we list down the given information. The weight of mother is 500 newtons. Kent is weighing 300 newtons. Charles is 250 newtons, and their father's weight is 600 newtons. Also in the figure, distances are indicated. Mother is sitting 2 meters from the center O, Kent is 1.5 meters, and father is also 2 meters. We see that, we do not know yet the relative distance of Charles from the center, nor his distance from his father. And that is what we are looking for letter A, and let us denote it as letter X. For letter B, we are going to solve for the magnitude of the reaction R, in the support. First, we must draw carefully the FBD of the seesaw. So this is the seesaw, and this is the location of the support O. Then, we indicate the downward forces caused by the weights of four persons sitting on it. Then, these downward forces must be balanced by the upward reaction force R, exerted by the support. Then we indicated the relative distance of all the forces from the support O. The distance of both mother and father from the support is 2 meters, while Kent is sitting 1.5 meters from the support. Since we label earlier the distance of Charles from his father as x, therefore, Charles is sitting a distance of 2 meters minus x from the support. At this moment, we are ready to solve for the distance x. So we use the equation for rotational equilibrium, that is the summation of torque, about point O is 0. Mother produces a counterclockwise torque, about point O, that is 500 times 2. Plus, another counterclockwise torque produced by Kent of 300 newtons times 1.5 meters. The reaction R does not create torque, since it already hits point O. Then father is doing clockwise torque, therefore, it is negative 600 newtons times 2 meters. Lastly, the torque produced by Charles is clockwise, so it is negative 250 times its lever arm, or distance from point O, to minus x. Then, we equate this to 0. From here, we solve for x, therefore x is 1 meter. It means that Charles should seat 1 meter in front of his father, so that the seesaw maintain its horizontal position. Then for letter B, we simply use summation of forces along y-axis equals 0. The reaction is equal to the sum of all these downward forces. So the reaction in the support is 1650 newtons. Well, that's it. Do you have any questions? I hope you clearly understood the solution to this problem. Now, it's your turn. Answer this exercise number 5. Two people carrying a uniform horizontal ladder, that is 6 meters long and weighs 400 newtons. If one person applies an upward force equal to 180 newtons at one end, letter A, how much force does the other man exert to maintain equilibrium? Letter B, at what point or position on the ladder does he exert this force? Good luck. In problem number 10, the support only exerted vertical reaction, since there is no any horizontal forces acting on the seesaw. In this problem, we shall see a pin support in which it exerted both horizontal and vertical reactions. Problem number 11. In a construction site, a 600 Newton worker is standing on a 8-meter long horizontal beam, weighing 200 newtons. The right end of the beam is attached to the wall by a pin connection, while its left end is supported by a cable that makes an angle 53 degrees with the beam, as shown in the figure below. If the worker stands a distance 2 meters from the wall, find, letter A, the tension in the cable, and letter B, the magnitude and direction of the force exerted by the wall on the beam. So let us write down the given information. The length of this beam is 8 meters and weighs 200 newtons. It is supported at the end by a cable which has an angle of 53 degrees from the beam. And this is the person weighing 600 newtons. His distance from the wall D is 2 meters. What we are going to solve is letter A, the tension in the cable, and letter B, the reactions by the pin on the wall, are X and are Y. Now let us draw the free body diagram of the beam. So this is the beam, and this is the pin, O. Then we indicate all the forces acting on the beam. We have the weight of the beam WB, 4 meters from the wall, the weight of the person WP, located 2 meters from the wall, the tension in the cable T, at the right end of the beam. And since that the tension T has an X component which is to the left, therefore the pin must exert a horizontal reaction Rx, which is to the right. The pin will also exert an upward reaction Ry. Now, are you ready to listen? I will show you how it is done. For the tension in the cable, we take the summation of torques about point O, equals 0. So referring on our FBD, the Y component of the tension creates counterclockwise force, so it is positive Ty multiplied by the lever arm, 8 meters. Then the weight of the person produces clockwise torque about point O, so it is negative 600 newtons multiplied by its distance from O, 2 meters. Then, the weight of the beam itself produces clockwise torque, so it is negative 200 newtons times 4 meters. Then we equate these to 0. Take note that the reactions Rx and Ry is not included in the equation since these forces are directly hitting the pin O. So from these equation, we simply solve for Ty. Ty is 250 newtons. We know that Ty is d sine of 53 degrees. Therefore the tension in the cable T is equal to 313.03 newtons. For letter B, solving for the reactions Rx and Ry, we begin with the summation of forces along x-axis equals 0. The forces acting on x-axis are Rx and negative Tx, equals 0. But Tx is t cosine 53 degrees. From here we solve for Rx. So the horizontal reaction exerted by the pin on the beam is 188.39 newtons. Lastly, for vertical components of the reaction, we use the summation of forces on y-axis. So we have Ry, plus Dy, minus 600, minus 200, equals 0. From here, we solve for Ry. So the vertical reaction exerted by the pin on the beam is 550 newtons. Are there any question, guys? I hope you can still follow. Just ask your teacher if you find any difficulties regarding our lesson. Okay, let us keep up. Let us give one more sample problem about equilibrium. Here, we are going to integrate static friction. Problem number 12. A uniform ladder of length L rests against a smooth, vertical wall as shown in the figure below. The mass of the ladder is m, and the coefficient of static friction between the ladder and the ground is 0.4. Find the minimum angle theta, at which the ladder does not slip. Let us analyze this. Imagine this is the ladder, that leans against the wall, at a certain angle theta. The length of the ladder is denoted by letter L, and has a mass, denoted by m. And since that, according to the problem, the ladder is uniform, we can assume that its center mass is located on its center. Assume that the wall is smooth, therefore, there is no friction between the wall and the ladder. The coefficient of static friction between the ladder and the ground is 0.4. What we are looking for is the minimum angle theta, at which the ladder does not slip. This problem seems difficult, since we have only one given information, and it seems insufficient information to solve this problem. In fact, we shall see that this minimum angle is dependent only on the coefficient of friction, not on the weight of the ladder. Now, let us draw the FBD of the ladder. So this is the ladder, and this is the minimum angle theta. We label the ends of the ladder as point A and B, respectively. Then, we indicate the forces acting on the ladder. We have downward weight of the ladder, W. In order to support the weight of the ladder, the ground will exert an upward normal force at point A. Due to the weight of the ladder, the end of the ladder at point A will tend to slide to the left. To prevent this, a static friction must be exerted on the ladder which is to the right. Since that the other end of the ladder at point B is in contact with the wall also exerted a normal force N sub B. Then it is also important to indicate the perpendicular distance of all the forces at point A. This is a shape of a right triangle, with hypotenuse equal to the length of the ladder L. By doing trigonometry, we see that the perpendicular distance of the weight of the ladder is half of the length, cosine of the angle theta. And the perpendicular distance of N sub B from A is L sine theta. Okay. I guess we are ready to solve. Always think that in equilibrium, we have three equations that we can depend on. The summation of torques equal to 0, the summation of forces along x-axis equals to 0, and summation of forces along y-axis equals to 0. Let us consider first, summation of forces along x-axis equals 0. Referring to our FBD, these forces are maximum static friction, and negative of the normal force, equals 0. But we know that the maximum static friction is equal to the coefficient of static friction, multiplied by the normal force at A. For the meantime, we solve for N sub A, so it is equal to the normal force at B over the coefficient of static friction. We label this as equation 1. Next, we consider summation of y-axis equals 0. From our FBD, we see that the forces acting vertically are N sub A, and negative weight, then this is equal to 0. But weight is also mg. Then, solving for the normal force at A, it is equal to mg. And we label this again as equation 2. After this, we equate equation 1 and 2, then, we solve for the normal force at B. Therefore, NB is equal to the product of the coefficient of static friction, and mg. Again, we label this as equation 3. Now, after we have utilized the equations of translational equilibrium, we still have one remaining equation, and that is the summation of torque about point A, equals to 0. From the FBD, we have only two forces that creates torque, the weight of the ladder, that tends the ladder to rotate clockwise, so it is positive NB, times its perpendicular distance L sine of theta. And this weight creates clockwise torque, so it is negative weight multiplied by its perpendicular distance from A, L over 2 cosine of theta. Then we equate this to 0. Take note that, N sub A, and Fs max are not included in the equation, since they already hit point A. From here, we will substitute equation number 3, we simply to solve for the minimum angle theta. The common terms are m, g and L, so we factor them out, and they can be eliminated from the equation. Simplifying further the equation, and using trigonometric identity for sine and cosine, the final expression will be tangent of the angle theta, is equal to 1 divided by the twice of the coefficient of friction. Wow, is it that amazing? we see that the angle is really dependent on the value of the coefficient of static friction only, not on the ladder's weight nor its length. Finally, we solve for the angle theta by getting the inverse tangent of the equation. Substituting the given information will give an angle of 51.34 degrees. So this is the minimum angle of ladder from the ground, at which the ladder does not slip. A slightly less than this angle, say 52 degrees, will make the ladder slide and fall. So every time you will use a ladder, you must take into consideration on this minimum angle to safely climb the ladder. Congratulations for reaching this last part of this course unit. We learned from Unit 1, the concept of weight. Actually, each particle of a body has weight. The total weight of the body constitutes the weight of all particle of the body. This total weight acts at a point called center of gravity, CG. It is the point where the body's weight is concentrated. The center of gravity of an object can be located in many ways. One of these is the plumb line method shown in figure below. The object is being suspended freely at 3 non-collinear points. A vertical line is constructed at each point using a plumb bomb, or any weight. In intersection of these 3 vertical lines is the location of center of gravity of the body. Another method is, by using the principle of torque or moment, as what we have discussed in equilibrium. It is more systematic and mathematical than the plumb line method. Here, the whole object or system is divided up into several number of smaller bodies of weight, mg. Each particle will have a set of x and y coordinates indicating its location, from the reference axis. The whole body or system has a total mass and its x and y coordinates is the location is the body's center of gravity, denoted by x sub cg and y sub cg. Using the principle of moment, the product of the total mass and its coordinate is equal to the summation of the product of mass of each smaller body and its coordinate. Therefore, the x and y coordinates of the center of gravity of the system is expressed as the summation of the product of the individual mass and the x or y coordinates of that mass, all over, the total mass of the composite body. The primary reason why it is important to locate the center of gravity of a body is to ensure the stability of a body or system. Stability is a measure how likely for a body not to topple over when force is applied. It depends entirely on the location of center of gravity, relative to the base or area of support on which the body is standing. For example, in the figure, a double-decker bus is stable on horizontal road, since its center of gravity is within the span distance of the wheels, which serves as the area of support. For an inclined road, the center of gravity is shifted towards one side of the wheels. If there is too much banking angle on the road, the bus becomes unstable, because the center of gravity will no longer within the area of support. Wow, congratulations for reaching this last problem. Problem number 13. A meter stick of uniform density is hung from a string tied at the 25 cm mark. A 0.5 kg object is hung from the zero end of the meter stick, and the meter stick is balanced horizontally. What is the mass of the meter stick? Let us analyze the problem. So this is the meter stick. The meter stick is balanced at 25 cm by the string, when a 0.5 kg weight hangs on zero mark of the meter stick. It means that the x-coordinate of the center of gravity is 25 cm. We know that the mass of the meter stick itself is located at 50 cm mark. What we are going to solve is the weight of the meter stick, denoted by m2. From the formula of the x-coordinate of center of gravity, x equals the summation m1 by 1 and m2 by 2, divided by the total mass, m1 plus m2. So from here, we solve for the mass of the meter stick m2. So m2 is equal to m1 times the quantity x1 minus the x-coordinate of the center of gravity, divided by x of cg, minus x2. Substituting the values, therefore the mass of the meter stick is also 0.5 kg. As expected, The mass of the meter stick is also equal to the mass of the object, since their distances from the string, which is the location of the center of gravity, are the same and equal to 25 centimeters. Now, this is also the last exercise for this course unit. Exercise number 6. Determine the x-coordinate of the center of gravity of a system of weights, composed of a uniform density meter stick of mass 0.4 kg, a 0.6 kg object, hung from the 20 cm mark, and 0.5 kg mass, hung from the 70 cm mark of the meter stick.